Underwater sensor networks, the second part. So, we have already understood the basics of underwater sensor networks, the usefulness of underwater sensor networks, and the basic architecture of underwater sensor networks. We have already understood those, the applications of them, the challenges behind the deployment of underwater sensor networks, and so on. So, let us now focus on the different deployment models for underwater sensor networks. So, when we talk about underwater sensor network deployment, there are different things that have to be kept in mind. So, first of all, network topology control, routing, boundary detection, these have to be kept in mind while taking care of the deployment issues. There are different challenges in underwater sensor network deployment. So, these challenges are with respect to that we have a 3D space, unlike in the case of terrestrial environments, and that so deployment itself, not only that the nodes have to be basically deployed in the 3D space, but also these nodes are subjected to different types of dynamic behavior in the water due to currents and tides and waves and so on. So, this is one thing. The second challenge is that the acoustic channel itself is is subjected to different things. So, there is number one, large propagation delay, there is high error rate, and there are multipath effects. So, these are the ones that we have already seen in the first part of this topic UWSN. So, in the part 1 we have already gone through these different characteristics of underwater channels, and additionally we have limited battery power available in the nodes. So, the goal of deployment is that we need to come up with some algorithms that will address the adverse channel conditions, the mobility of water, and energy efficiency of the sensor nodes. So, based on different criteria, the underwater sensor network deployment algorithms can be classified into 3 types: static deployment, self-adjusted deployment, and movement assisted deployment. In static deployment, again you can have random deployment or regular deployment. In self-adjusted deployment, you have uniform coverage deployment or non-uniform coverage deployment, and then you have the movement assisted deployment. So, broadly 3 classes of UWSN deployment: static, self-adjusted, and movement assisted. So, in static deployment, the sensor nodes are static after their deployment with the considerations of the practical reasons such as the deployment cost and algorithmic complexity. So, as the name suggests over here again, so these sensor nodes, somehow you make them static, either you make them static on the ocean surface, just below the ocean surface, you tag them through some buoys or something like that, or you tag them in such a way that they are not going to move, right. So, you make them static. So, this is one possibility, or you put them on the ocean floor, and that way they can be made static. So, typically these are like 2D deployment mechanisms. So, either ocean floor or ocean surface. So, in 2D underwater sensor networks, the sensor nodes are usually deployed only on the water surface or at the bottom of the monitored region, but 3D deployment is also possible for static, where the sensor nodes float at the different depths of the ocean to observe the entire monitored region, and the sensor nodes do not actively change their positions after initial deployment. So, basically the relative displacement of these nodes, they remain the same, right. So, these nodes, they are basically fitted with certain mechanism by which even if there is a ocean current that will hit it, it will again come back to its original pre-configured position, right. So, and these nodes are going to float at different different points in the ocean column. So, 2D is more typical for static UWSNs, 3D is also possible, and both of these are using both of these models one can have static UWSN deployment. So, random deployment is one where basically what happens is it's more of a like practical way of deployment, as this name suggests, that randomly at different positions you are going to deploy these sensor nodes. And in regular deployment, basically it is determined. So, maybe some kind of a polygonal shape is considered, or a polyhedron polyhedral shape is considered, and these sensor nodes are anchored at the different vertices of these polygons and polyhedrons, right. So, the advantages of static UWSN deployment algorithms are that they are easy to deploy, they are energy efficient, and they do not need any mobile nodes to participate in the deployment periodically. The disadvantage is that they cannot deal with the real time event processing in large scale underwater sensor networks. Self adjusted underwater sensor network deployment is the second type of deployment, where the sensor nodes are capable of adjusting their positions in underwater after initial deployment to satisfy certain requirements. Here each sensor node is attached with a floating buoy, and the sensor nodes can adjust their depths by controlling the length of the wires. So basically, so you place them somewhere, these sensor nodes, they can self adjust depending on how the buoys are programmed on which the sensor nodes are affixed, and so these nodes, they can adjust their positions by themselves, and they are going to maintain the positions in the ocean column. The advantages are like this, that the depth adjustment system enables the nodes to be positioned with the desired topology, which improves the network connectivity over the monitored region. So, this is one advantage. The second advantage is that the relocated sensor nodes at different depths based on local agreements, and that can effectively reduce the coverage overlaps among the neighboring nodes. So, this relocation, basically these relocation mechanisms are of these nodes at different depths that can basically improve the overall performance in terms of coverage, etc., and that way the overall performance of the network also gets improved. Uniform coverage and non-uniform coverage sensor network deployment. In uniform coverage, the sensor nodes are initially deployed at the bottom of the ocean. Each sensor node is assigned a target depth, and the nodes float to the desired positions to achieve the target coverage ratio. In non-uniform coverage, the sensor nodes adjust their positions according to the dynamic environments and targets, and the event area is covered in an optimal manner by using optimized algorithms such as game theory or different types of optimization and so on. So, in movement assisted underwater sensor networks, AUVs and ROVs, etc., are also deployed with other sensor nodes. So, these AUVs, ROVs, etc., UUVs, they basically patrol over the monitored region under predefined trajectory to cooperate with the sensor nodes to execute the desired task. So, the sensor nodes are deployed at different places, and these AUVs, ROVs, etc., they are going to move around these sensor nodes, and they are going to help these nodes, these sensor nodes which are deployed, to help them to cooperate or communicate with each other. The sensor nodes can be attached to the mobile nodes, and they can be shifted to some desirable positions as well after initial deployment. So, you can basically have one of these sensor nodes or a couple of these sensor nodes affixed to these AUVs, ROVs, etc. So, when they move, they can also take them away, take them to the new location, and so on. So, this is movement assisted underwater sensor network deployment. Now, let us look at a specific type of underwater sensor network deployment algorithm that is proposed, which is the self deployment of sensors for maximized coverage in underwater acoustic sensor networks. This particular paper was published by Akaya and Newell in Computer Communications Journal in 2009. So, these are the features of this particular deployment algorithm. The current node deployment in underwater sensor networks is mostly manual and centralized. Sensors are placed manually with tethers from the surface station or anchors from the seabed. These are the considerations that this particular algorithm by Akaya and Newell basically take. Such deployment may not be feasible in applications where deployment region is not accessible due to enemy threats or existence of mines in underwater tactical surveillance applications, and such deployment scheme requires additional time and cost, particularly when the volume of the monitored region is larger, and there is a need to drop the sensor nodes from a flying vehicle or from a fixed ship to the area of interest. So, these are some of the characteristics of this deployment algorithm by Akaya and Akaya and Newell. This is the kind of consideration that was meant in their algorithm. So, they have the onshore sink and they have the ocean surface. On the ocean surface, they have the surface station, and the surface station basically there are different nodes on the sensor nodes which are basically floating all around in the ocean column, and this is the acoustic mode of communication. And from this basically there is no data are brought to the this particular surface station, and from the surface station to the onshore sink it is sent by RF communication. This is the overall architecture that is considered by Akaya and Newell. So, self deployment of sensors for maximized coverage in underwater acoustic sensor networks. So, there are in this particular scheme, Akaya and Newell scheme, there are 4 phases that have been considered: the clustering scheme, clustering phase, the grouping phase, the depth adjustment phase, and additional rounds phase. So, in the clustering phase, basically after initial random deployment, the sensor nodes are clustered based on their node IDs, and each node in a neighborhood basically picks the highest ID in that neighborhood as its cluster ID. So, the cluster IDs are selected. The nodes are initially deployed randomly, and the clusters are formed. The cluster IDs are selected, and the node with the highest cluster ID is selected as the leader of the cluster. So, this is initially this is the initial network, and from this you are going to form different cluster IDs like this, right. So, these are the different cluster IDs, and from these cluster IDs one can get the this is the cluster head, right. So, one can calculate the cluster heads. So, once these nodes are clustered, the clustered leaders need to determine the possible coverage overlaps within a cluster. So, these nodes are grouped within each cluster based on the coverage overlaps with their neighbors. The age between the two nodes indicates that there is a sensing coverage overlap among the two nodes, and they need to be sent to different depths to eliminate this overlap. So, this is how basically they want to maximize the sensing coverage overlap, and they want to send they are first of all they are determining that there is some kind of an overlap, and then they are going to send them apart as much as possible. So, at the end of this phase, these two nodes need to have different group IDs, GIDs, which are denoted through different colors. So, these different group IDs are formed: GID 1, GID 2, and so on and so forth. So, these would look in the this is the depth view of these group IDs and the corresponding clusters, etc. And this grouping of these nodes, they are based on the sensing coverage overlaps. So, there are other phases after the clustering and the grouping phase. There is the depth adjustment phase. So, to improve the coverage overlaps and the overall 3D coverage, the depths that will be assigned to each group are computed using this particular formula. So, the space between two groups is should be maintained as d by g plus 1, where d is the depth of water and g is the number of groups. So, this spacing makes sure that each layer is d by g plus 1 distance away from each other. So, then the next phase is basically the additional rounds phase. After initial deployment, the nodes from different clusters are assigned the same depth, and they can still have coverage overlaps. Nodes continue to attempt to move away from each other vertically. The movement will need to be stopped when there is no significant improvement for coverage or a certain number of rounds is achieved. So, this was one very important deployment scheme that is known, and the other one is basically that this is proposed by Han, Zhang, Xu and Rodrigues in IEEE Transactions on Industrial Electronics in 2015. So, here basically this particular work it is more focused on the impact of the deployment strategies on localization performance in these networks. So, in this work, the impacts of the different deployment schemes on localization and network connectivity are investigated, And the different deployment schemes that are considered are the random deployment, the cube deployment. Cube deployment means that cubes are considered, and at the corners of the cubes the sensor nodes, the anchor nodes are placed. And regular tetrahedron deployment means that the tetrahedral shapes are considered and the nodes are placed at the different vertices of the tetrahedron, and these are going to act as the anchor nodes. So, the sensor nodes are deployed at different depths depending on the deployment scheme. And so the random deployment, the anchor nodes are deployed randomly in a 3D monitored region. The ordinary sensor nodes are deployed randomly in the 3D monitored region as well. In a cube like deployment, the sensor nodes are deployed at the vertices of the preposition space filling cubes. The ordinary sensor nodes are deployed randomly around those, and in the regular tetrahedron deployment, the anchor nodes are deployed at the vertices of some prepositioned regular tetrahedrons, and the ordinary sensor nodes are deployed randomly around them. So, this is how it looks like. This is the cube like deployment over here, and where this is like the one cube unit. So, you have these anchor nodes which are placed in a cube at the vertices of these cubes, at the corners of the cubes, and these ordinary sensor nodes basically are placed randomly around them. And the similar kind of thing is shown in a different way. Over here we are considering a regular tetrahedral unit, and where the anchor nodes are placed at these different vertices of the tetrahedron, and the random nodes are placed around these nodes. So, different simulation parameters were considered in order to study the performance of these. So, localization ratio is one. So, localization ratio is about the ratio of the number of localized ordinary nodes to the total number of ordinary nodes. Localization error is the other parameter that was studied, which is basically defined as the average distance between the estimated coordinates and the real coordinates. And the network connectivity, which is the ratio of the number of sensor nodes that can communicate with the other sensor nodes to the total number of sensor nodes. So, with this we come to the end of underwater sensor networks part 2, and so here we have seen that there are different deployment strategies that have been proposed in the literature. And so, these different, it is not like one type of deployment scheme is used for serving different applications. There are different schemes are used for different applications and so on. So, it is also not that 2D scheme is better or a hybrid scheme is better. So, it could be that in some cases like a 3D or a 2D or even a hybrid scheme could be better than the other schemes that are available. So, these are some of the references for this part of the lecture. Thank you.